Swayam Prabha. Digital India. Educated India.
As I said that this electron counting rules of in organometallic chemistry, I am sure that this topics is known to you that I am planned to teach today. So, first of all, most importantly, what is important is you need to understand the molecule first. Suppose if I give you a simple molecule, I am sure that you all know. Tungsten hexacarbon, very well known. So, first you need, like in your bank, no, if you open an account, so everybody they ask you KYC. What is it, KYC? Know your client. So, that means you go open an account, they need to know who are you. So, here what we need is know your molecule, okay. Or you can also call know your compound, okay. So, to know your compound, there are two components is very important. One is, can you tell me what are they? To know your compound or molecule, what you need to understand first? Simple, no? What you have here? Huh? Speak loud. Very good. Metal and ligand. So, you need to understand what is this metal. What is this metal? Tungsten, you all heard about it. Chromium, molybdenum, tungsten. So, this is in that chromium, molybdenum, tungsten. So, now you know your metal. Now, you need to know your ligand. What is this ligand? Carbonyl. And this is a very well known ligand. But in exam, you may not get so simple ligand. So, you need to understand your metal and the ligand, and rest of the things this will take care of it, how to count the electron, so on and so forth. Okay, so I am going to give you some different types of ligand. Okay, they are, first one is your X type ligand. What is X type ligand? X types ligands are like, suppose if you have a metal, you have a ligand, and if they form this, so one electron from here, one electron from here, you get this. So, X type ligand, like you have a metal here, I'm a ligand. So, that means metal gives one electron and the ligand gives one electron and it forms this bonding. So, these are called X type ligands. So, which are the ligands that give one electron? Halides. So, that is why they always call X minus, no? Cl minus, Br minus, H minus. So, these are called X type ligand. Another type of ligand called L type. L type ligand, in which what happens? You have a L type ligand in which metal does not give any electron, but the ligand gives 2 electrons. And in this case, can you tell me some ligands that gives 2 electrons? Huh? Carbonyl, very good. Any other ligand? Huh? oxalate. Oxalate, I would, well, I mean, although it gives electron, but in this case, a little different than that. Any other neutral ligand, it could be phosphine. Yeah, you can. NH3. Okay, so what happens? In this case, it ligand contributes electron and you get the bonding. And the last one is your Z-type ligand, in which the metal gives 2 electron. The Z-type ligand, in which metal gives the ligands a little bit. Okay, here you have a ligand and you get, so this metal could be something, you know, starting from early transition metal all the way up to the nickel, in which you have a metal gives electron, ligand does not give. So you have a 3 different types of ligand in which both metal and ligand gives electron, and the metal gives electron. And what are the typical example in this case? Can you give one? Huh? Like, how many of you heard about boranes? Please don't talk. If you have any questions, please ask me. How many of you heard about boranes? Diboranes, B2H6. So, if you have this one, BH3, you heard about BH3? You have seen? You have seen borane? Never. Borane is highly inflammable. No one have seen borane. But you can isolate them. You can isolate them. So, what is the electron count of boron? Electron count of boron is 3. So, you have 3 electron. So, what is the typical thing that we all learn in organic chemistry? That is the octet rule. So, how many electrons here now? 6 electrons. Hydrogen also gives 1 electron. So, this is electron deficient. So, boron is the only element in the periodic table that does not follow that octet rule. They follow sextet rule, 6 electron rule. So, that means this require 2 electron, and these 2 electron can be given by any, like, to isolate this boron, mostly what you need 2 electron from somewhere. That's why boron always, so you can buy it in the market and they are sold with like THF adduct or amine adduct. So, this is called, like, if you have the tetrahydrofuran, and so this 2 electron, it goes to the boron and it gives 8 electrons now. Okay. So, this is on that Z type, or it could be aluminum also. All right. So, you know now typically these ligands. So, there are other ligands also other than this X, L and Z type of ligand. Suppose if I give you, you all heard about cyclopentadienyl anion, Cp minus. Okay, you have cyclopentadienyl hydride. So, you can, if you treat this with sodium, what happens? You get Cp minus, right? So, how many electrons this one? Cp minus considered to be how many electrons? 6 electrons. So, you can consider this as 3L. L-type ligands means 2 electron. So 6 electrons means 3L, right? So there are now there are many other ligands, like if you have a allyl ligand, it can be considered as XL, or it could be L2 or X2. Many things you can do. Like if you have a benzene, benzene can also coordinate with the 6 pi electrons with like you heard about arene chromium, chromium CO3 eta 6 benzene, right? So this gives 6 electron. So you can consider this as a L3. Good. Now I am going to give you some examples. Okay, one more thing before I get there. You heard about this ligand. Another thing can be connected with the sigma type ligand, pi donor ligand, pi acceptor ligands. They all heard about it. So sigma ligands in which this gives 2 electron to the like along the axis, and if you have a pi donor ligands, this give electron from the ligand's 2 electron goes to the d orbital of the metal, and in the case of your pi acceptor ligand like CO, in which what you are getting here is if you consider this, and you have, let's say, your carbon monoxide. So this 2 electron goes here. So it's the pi star orbital of the CO. Okay, so this is pi acceptor ligand. If it is the other way, your pi donor ligands like halides, it goes to the vacant d orbital of that, and so on and so forth. And you also have seen how the carbon monoxide get along the axis with the dg square and dx square y square, and you get a synergic type of bonding in the metal carbonyl complexes. So you have all 3 different types of bonding in which you see this pi donor, pi acceptor, and the sigma type of bonding. Now, so now I am coming to give you some examples, particularly first, I do not know, as I said again, that probably for the electron counting rules where Mingo's, Ware's rules are considered, this could be a little tough, but let me go with, you make the base little stronger for you, then you will see how you can take it further. So first we will do the 18 electron rules. You all heard about 18 electron rule. Very good. What is that? Speak loud. It's okay. I mean, this is a class where you need to interact, then only you learn. What is 18 electron rule? Anyone can tell me what is a, see, 18 electron rule is very well known, everyone heard about it. But what it is? Huh? You do not know what it is. (18) electron rule. So inorganic, how many classes you had? Inorganic, who taught you here in IIT Madras? How many teachers? So there was nothing on 18 electron rule? So then tell me, what is 18 electron rule? If a compound contains 18 electron, it will be highly stable. It's okay, but like you need to justify further. What is 18 electron? So suppose you have 1 mark. What is 18 electron rule? Describe. Huh? Okay. So I'll give you a ligand. Metal and ligand contribute. What is the electron count here? What? 18? How many electrons? Tungsten 6, chlorine 6. So this is 18 electron? So that's why I'm saying what is 18 electron. Okay, I'll tell you 18 electron rules made for only metal carbonyl complexes. Okay, number 1. And to do that, what it describes that if any of the metal carbonyl complexes contain 18 electrons from the contribution of the metal and the ligands, then that particular compound, what you said, is stable. If a molecule containing all, you name any metal carbonyl, or just see any of the molecules that is been listed there in the textbook, does not contain 18 electrons, so that means they are not stable. Okay, I had shown you so many examples of them. So it is not meant to be 18 electron rule. There are many examples, particularly with the inorganic complexes. All these transition metal complexes, they are not supposed to follow 18 electron because that is not meant for it. It meant for only metal carbonyl. Now you name any metal carbonyl that is coming to your mind. Start with, let's say, what are the different metal carbonyl you know? Nickel, very good. What is the electron count? Nickel 10, carbon monoxide 8, 18 electron. FeCO5, 18 electron. 8 plus 10. Cobalt 2CO8. There are two metal, but again it's a 18 electron. If you have a manganese 2CO10 or many of the other monometallic carbonyl complexes, they all follow that 18 electron rule. Now, to justify this, vanadium CO6, what is the electron count? 18? 16? So you are having problem how many vanadium gives electron. Vanadium gives 5 electron. 17. So now 18 electron rule, if you justify, that means this molecule is not stable. In fact, it is not stable. It is very unstable. It needs what? Very good. How you get electron? You give it like, okay, take 1 electron from me. How you give electron to the compound? By? How you give electron? There is a electron generator or what? How you can give 1 electron to this molecule? But how? You give sodium. No. Sodium gives electron, no, and it becomes Na plus. So if you like to give electron, you have to treat this with sodium and gives electron. Like naphthalene, no? If you put a sodium, it becomes like a green color because it gives electron and the many things happen. Okay, so that means you need VCO6 minus, and then this molecule is very stable. Now to justify this with another angle, suppose if you have manganese CO10, manganese CO5, what is the electron count? 17, 7 plus 10, 17 electron. So you can also give electron to this manganese. Otherwise, you can do one more thing, you can dimerize this one. And you can get 18 electron on both these, similar to that of the cobalt 2 CO8. So now your question could be why the vanadium does not dimerize. It can also dimerize, right? But it doesn't, does it? So this is a question in your textbook, you can look at it. That why the vanadium CO6 does not dimerize to give similar type of molecule as that of the manganese 2 CO10. Okay? Okay, so these are all very simple examples of a 18 electron rule and count the electrons. So you may not get so simple question in your exam. So I will give you some examples and I want you to calculate, okay, and justify. First one is Cp2 tungsten CO2. I want you to draw the structures. All the molecule contain 18 electron rule. This is one. Another one is tungsten 2 H2 CO3 So this is the second example, and the third example is so what I want you to know is first you have to show me how all these metal are 18 electron species. So let's do the first example. So you have a 2 carbonyl. So you need to first understand the ligands. So you have a cyclopentadienyl ligand and you have a CO2 ligand. And what I want is this one should be 18 electron. How you can make it 18? How you can make this metal 18? So if you Cp how many electrons gives? 6. If you remove one hydrogen, you get a Cp minus and you coordinate with the metal, it will be 5 electron. Cp minus is a 6th electron. But when it is a Cp, it gives to the metal is a 5 electron. So Cp is a 5 electron. So you have a 2 Cp 10 electron plus tungsten 16 plus 4, so 20 electron. So that means you have to make this Cp as eta 5 hapticity. Of you heard about hapticity? Hapticity means like if you have this, let's say this one. Okay, so the cyclopentadienyl can participate in eta 1, eta 3, eta 5, different types. Suppose if you have a cyclooctadiene, it can coordinate with it. Like if you have this kind of system, okay, so it can coordinate with this, it can coordinate with both of them. So it's a eta 4, and if it coordinates only with that, it will be eta 2. So that means Cp can coordinate, in this case, the structure of this molecule would be So you have a tungsten, this is eta 5 completely, and another one would be eta 3. So eta 3 and eta 5 at 8 plus 6, 14 plus 2 CO. So your CP, so there are many questions. This is a typical, like undergraduate BTech question we always ask. Draw the structure of CP2 tungsten CO2. So use your hapticity. So it will be hapticity 5 and hapticity 3, and that can give you a 18 electron rule. What about the other two examples? Eta 2 hydrogen. What is eta 2 hydrogen? Sir, how are you? Hello, how are you? You are not reacting, not answering, nothing. Difficult? Easy? Okay. What's your name? Narendra. Tell me first one. What is eta 2 hydrogen? You know hydrogen. What is it? H2, no? H bond. You have hydrogen. So eta 2 hydrogen means you have a hydride, this, and it can give 2 electrons to the metal. This is called eta 2 mode. You can break it and it gives H minus. Okay, the first one, you have your tungsten, this, that is eta 2, and the rest of the things are fine. CO3, and you have 2 phosphine. So phosphine gives how many electrons, Narendra? Very good. So you have CO3. So total 2 phosphine, 3 CO, 10 electron. Tungsten gives 6 electron, 16 plus eta 2 hydrogen, so it's 18 electron. So if I ask you to draw the structure of the first one, it would be like this. PR3, PR3, CO, CO. All right? It's clear? Who didn't understand? Okay. So I'm very bad of, like in my class, asking questions to all the students. So if you don't want, then I will not ask you question. I'll just simply teach and go. Which one you want? Ask question. Okay, then you start with you. This molecule, tungsten, what is the oxidation state? You know how to calculate oxidation state. To calculate oxidation state, you need to understand, I told you in the beginning, know your ligand. So what is the ligand here? Hydride. Eta 2 hydride means it is not like H minus. It's like a alkene, no? You have a pi electron, alkene, acetylene. It just simply donate. Like G salt, platinum, ethylene, that gives 2 electron. So in the hydride, it gives 2 electron like this. Phosphine, what is the charge of phosphine? Charge of phosphine. It's a neutral ligand. Phosphine neutral, carbon monoxide neutral, hydride neutral. What is the then oxidation state of tungsten? Everywhere is a neutral. Then where is the oxidation state is 3? It's a 0. Hydride 0, this 0. So there is no charge, isn't it? So what is the electron count of tungsten? 18. What is the oxidation state? 0, right? What is the d electron configuration? You all know what is d electron. D1, D2, D3, D5, D6, D7, D8, D9, D10, D11, D12, D12, D11, D10. Good. So what is that here? D. Yeah. So basically they are very strong ligand. No, if they push the s orbital, so it will be D6. It's a D6. Very good. Now I made your job much easier for the third example. Go ahead. First you have to draw the structure. What's your name? Saundarya. Tell me, what is the structure? This is not eta 2. This is hydride. So it's like this. Okay, and other things are 5 ligand. So you have 2 phosphine, 3 carbon monoxide, 10 electron. Tungsten gives 6 electron. 2 hydrogen gives 1 electron each. Sandra, you tell me what is the ligand type here? Anyone? Very good. X-type ligand. X-type ligand, how many electrons contribute? Very nice. What is the electron count of the tungsten now? Tungsten. 18. 18. Now, what is the oxidation state now? What is the oxidation state now? Who said +2? Raise your hand. You raise your hand, you did a good job. +2 because X-type ligand gives -1. How many X-type ligands are here? So it will be +2. So in the first case, you have noticed although there are 2 hydrogen, but that was in the eta 2 mode gives no charge. In this case, hydrogen breaks into hydride and become a X-type ligand, and you get 2 charges here. In both the complexes, it follows 18 electron rule. Clear? Good. Okay, now I will give you some further examples of this is it will be very interesting. I'll see how many of you can make it. I'll give you a last example before I go to the other one. C5H5. Okay, first you tell me how many electrons of nickel, what is the oxidation state, and what is the d electron configuration. What is the electron count? First one is the electron count. Then Dn configuration and oxidation state. Bolo. First is electron count. Very good. 20 electron. Can you explain? Very good. Excellent. D electron configuration? You have to just tell me D. Only D. D8. Very good. And what about the oxidation state? Cp is not neutral. Cp is minus. 2 minus means 2 plus. So nickel 2 plus 20 electron, and so what is this molecule called? You all heard about it. Nickelocene. You all heard about ferrocene? What is ferrocene? This is nothing but Fe. Ferrocene you heard about. What is the electron count now? 18 electron. That's why this ferrocene is extremely stable. Nickelocene is not. Is extremely unstable. Cobaltocene, how many electron? If you have a cobalt, 17. Sorry, 19 electron. Thank you. 19 electron, again this molecule is very unstable. So to make this molecule stable, what you need to do, Narendra? You remove one electron. So you make it plus. To make the nickel, you have to remove 2 electrons. Okay? So this is the power of 18 electron rule. So there are many more examples. I will give you some more, and you will see how nicely 18 electron rule can let you, decide whether the molecule will be stable or not stable. Okay, now I will before I move into your some more examples. One of the very important properties of this metal carbonyl is your infrared stretching frequencies, IR. So how you can characterize your metal carbonyl molecules? One of the very important spectroscopic data is your infrared spectroscopy. Okay, now if you have, let's say, FeCO5, if you have a cobalt 2 CO8, if you have vanadium CO6 minus, if you have, let's say, FeCO4 2 minus. Typically, the infrared stretching frequencies for the carbonyl in general, if you know CO gas, okay, CO gas is very poisonous, you all know. CO gas, if you take a simple stretching frequencies, it comes around 2300 something. It comes at so around that only. But when the carbonyl is attached to the metal and you get a terminal, let's say this molecule. This, what is the geometry, anyone knows? How many ligands you have? So, okay, this is something I will come back a little later. So, depending on the number of ligands, you can decide what would be the geometry. If you have a 4 ligand, what is the geometry? Tetrahedral. There is one more. Huh? Trigonal pyramid. What is the geometry? This is a trigonal pyramid, tetrahedral, almost same, no? So, what is the other one? What is this? So, Now you know the butterfly. But this is also 4 ligand. So you have a tetrahedral, square planar, and butterfly. 5 ligand, butterfly, yeah. What is your question? Okay. 5 ligands. Very good. Next. You said it, something like that. Speak loud. Pentagonal, pentagonal what? I heard it. Pentagonal what? You have 5 ligands. You said trigonal bipyramid. Correct. Any other geometries? Square pyramid. Any other geometries? Square pyramid, pentagonal bipyramid, perfect. What else? Pentagonal planar, that also possible. Suppose if you have, let's say, this kind of very rare, where all the ligands will be in one plane and metal will coordinate with all of them being on the same plane. So it's very rare, but typically square pyramid and a trigonal pyramid, bipyramid. So these actually in the same. FeCO5 molecule actually fluctuate between square pyramid and trigonal bipyramid, and the difference between these two geometries, like if you are talking about, suppose if I ask you to stand on one leg, how long you can stand? 1 hour, 2 hour, 3 hour? How long you can stand? 1 hour you can stand, not a problem. But you cannot stand for a long time because it's a stability problem. So the TBP, if you have a square pyramid and you have this trigonal bipyramid, these two geometries are actually highly fluxional. The energy difference between these two states are 5 kcal per mole. Very, very low, so just goes back and forth, back and forth. So whatever it is, let's say one of these geometries. So that means all these CO ligand, and you have in the middle you have the Fe. So these are all terminal CO. So these all carbonyl ligands that is attached to the metal are terminal, and these terminal ligands typically comes around 200 to 1900 centimeter inverse. So based on your centimeter inverse, the band at wherever it coming, you can tell that these are all terminal CO. If the carbon monoxide, if you have a two metal, this is also possible. It's called mu2CO. This is called mu-CO. It's also possible that can coordinate with the 3 metal. This is called mu3CO. So depending on the like a bridging mode, the CO frequency will go further down, down, down. And there is a reason for this, all these lower stretching frequencies. So you have, as I shown to you earlier, and you have your COs here. So what I was trying to tell you is that this electron, from this 2 electron, it goes to the pi star vacant orbital of the CO. And the metal, if you have electron rich, it can gives more electron pumping to the pi star with the empty orbital. If the metal has a negative charge, so that means this can gives more electron to those. So that means what? This metal carbon bond becomes stronger and the CO bond gets weaker if you have a more back bonding. You understand what the concept? If the metal has more negative charge or electron rich in the nature, so that means there will be more back bonding to this pi star orbital of the carbon monoxide. and eventually they will make the metal carbon bond stronger and CO bond weaker. So if the CO bond gets weaker, your frequency get lower. Okay, so that's been reflected. So now if you have a one metal, you have two metal, you have a three metal coordinate with the CO, so that means it will be more back bonding to the CO, and that's why this CO frequency goes further down. So you have a terminal CO, you have a bridging CO, you have a mu3 CO, the CO stretching frequency goes down, 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 down like this. Okay? Now I'm coming back to this one. So if I ask you to comment on these CO frequencies, you will be able to tell, because this has a negative charge, more negative, more back bonding. If you have this one is also minus, it has a 2 minus, you have a single minus, it would be less back bonding. And this one has a bimetallic system, you have a monometallic system. So accordingly, you can comment on their stretching frequencies. So this is one parameter, like when we talk about an organometallic compound of the metal carbonyl, this is very important parameter. Now, if you have, let's say, molybdenum CO6, molybdenum CO6, that's the one example I had given in the beginning. Now, if I remove one of the carbon monoxide by another 2 electron ligand, what is it? Let's say phosphine. Okay, I remove this one with one phosphine ligand. You can do it if you do the photolysis. If you add this, it will. Let's say this is PPH3. Or if you do with now you have got two types of molecule. One, you just replace CO with another 2 electron ligands with phosphine. Now in both the cases, if I ask you to comment on the CO stretching frequencies, which one would be lower? This one or this one or this one? Let's say this one at, I don't have the exact value with me, let's say around 2000 centimeter inverse. So this would be a lower or same or higher. So again, know your ligand. So what you need is, the concept is the same, whether these two molecules will show stronger back bonding or the weaker back bonding. Stronger back bonding, correct answer. Why? Phenyl groups are? No. This concept is something different. It's nothing to do with phenyl, but something to do with the phosphine ligand. Saundarya, tell me. Carbon monoxide also that way can. So you need to compare one property called sigma donor properties. Now CO and phosphines are better sigma donor than the CO ligand. If it gives electron to the metal, eventually you'll have a stronger back bonding. So that means this would be further lower. If you compare this, the value of those two cases would be lower. Now if you compare this one and this one, which one would be lower further? So that means you need to know PME3 and PPH3, which is a better sigma donor. These are all textbook thing. I'm sure that all of you read this. Phosphine ligands, you never heard about of those cone angles or the sigma donor property. These are very straightforward questions, no? So PME3 is a better sigma donor than PPH3, Better sigma donor means it gives more electron to the metal and eventually get a very stronger back bonding, and eventually CO stretching frequency gets lower. Okay, clear? So these are all like there, you all have the Atkins inorganic textbook or BD Gupta. Which textbook you have? Which are the textbook you follow? Your teacher has given some textbook. And what are the textbooks? Huh? You don't have any textbook. No, but in general, organometallic chemistry, there would be a textbook, right? I'm sure that when your teacher had given some reference textbook. No? Organometallic textbook you don't follow, or you just follow internet? See, I cannot tell you that I'll offer 30 textbook to you. It will be too much, but these books are available e-copies. So you are here up to 19th, right? Yeah, but I am traveling this afternoon. But I'll see to it that I'll talk to that Anberson, Professor Anberson, and if you can send you that e-copy one of the textbook where all those things would be there in the. But I'll see. Probably I'll coordinate with the that person or the Professor Anberson. You have received email from Professor Anberson, so I think he will send you those textbook when you get home. Okay. So otherwise, like whatever things you have taken note, but these are not enough. There are so many things you need to solve, question answers and all. Okay, these are all there in your textbooks. So after MSc, what you want to do? PhD or B.Ed, MPhil, PhD outside, job, or teaching in a school? What, you are not eyeing for any higher studies, are you? So if you are going for a higher study, I'm sure that many of you will not be interested in inorganic chemistry. No, sir, enough. This is my last class. Huh? So anyway, if you are interested, then I think this textbook are necessary so that you can gain interest on that particular topics. More, see that I became inorganic chemistry because of my teacher in the BSc. I was so much fascinated with his teaching, everything. So if you have in school, there are some of your teacher that may be very much into interest in a particular subject, and slowly you develop that interest in a particular subject or particular topic or a broader inorganic, organic, physical chemistry. So you need to, you like a particular food because you got used to it, the taste of that. Okay, all of a sudden if you give a food, you may not like it. So you need to grow interest with that particular subject with all the different things, so on and so forth. So the textbooks are very important one. So the next one is I thought of giving you a problem, but let me see how you can do this. Okay, you have one compound eta 5 C5H5 chromium CO2 . Okay, so I am giving you a problem. You have to deduce the structure of the molecules I am interested in. So this is a molecule. What it says that in the problem, it obeys 18 electron rule. Okay, it obeys 18 electron rule. This is a dimer. You see that overall it's 2. This molecule obeys 18 electron rule. On treatment with CO, so that means you are passing carbon monoxide gas, and this molecule, so this is A, excess CO gas, you are getting molecule B, and then this is also 18 electron rule. Okay, now if you do a photolysis of A, you getting molecule C. The first one is 18 electron rule, in which you have all this carbon monoxide at terminal. Terminal means in which you have 2000 to 1900 something the stretching frequencies. Now the molecule B, this is also 18 electron rule. You also have all terminal CO. But molecule C, this one has a bridging CO. Okay. Deduce the structure of ABC. This is a little difficult question. Now, can you comment on it how you will approach this problem? This kind of problem you may expect in your competitive exam. Now, the first one is you need to, and molecule B and molecule C have a same number of metal-metal bonds. Okay, the way you need to approach this problem is first you need to know what is the structure of A, then only you can go. So, this is a dimer, it's a chromium, you have eta 5 CO, okay, that molecule structure is chromium, 2 CO here, and you have eta 5 CO. Now, can you tell me whether this molecule follow 18 electron rule or not? 2 CO, 4 electron, Cp 5 electrons, so 9. Chromium how many? 6. 6 plus 9? You have 5 plus 4, 9 plus 6, 15. Plus you have one bond, that is 16. So this is not 18 electron. So to make it 18 electron, what you need to do? Speak loud. How? Huh? I cannot give you anything. With that only you have to work on it. How I can make this molecule 18 electron? You have chromium bond. You have 2 CO, 1 Cp. This is 16 electron. How I can make it 18 electron? You can make metal-metal triple bond. Simple. 18 electron. Now, if you put excess of CO gas, what will happen? Excess of CO gas means what? You are giving electron. So that means your triple bond will breaks up and will add one CO in both. Right? And what is the structure in this case? You get a chromium, instead of this. become chromium-chromium single bond. So you have a 3 CO plus 5, 6 plus 5, 11 plus 6, 17 plus 1 bond 18. So this is the structure of molecule B. Now if you do the photolysis, and as I told you earlier that molecule C and molecule A having the same number of metal-metal bond. So that means this also has chromium, this. But in this case carbon monoxide is in the bridging mode. It's not a terminal. So I think bridging mode, if you do the bridging mode, what will happen? Of this 4, 7 should be how many? 3 COs. How many electrons now? So you have a 5 plus 6, 11 plus 3, 14, 14, 15, 16, 7. So this is a, oh, I think I forgot to tell you that molecule C actually is a 17 electron species. Okay, so this is a 17 electron species, others are 18 electron species. So this one, what I was trying to tell you is that the 3 of this, so if you do photolysis, like if you take any metal carbonyl and if you do the photolysis, it releases CO gas from the compound. This is the nature of the reaction. Thermolysis and the photolysis, you have a different, like wavelength you can do. So that means, as I told you earlier, if you photolyze, the CO gas will go out. You have how many CO gas here? Sorry, CO ligand? 4. So you become minus 1 CO, become 3 CO, but that get into a bridging mode and leads to the formation of this. So this is something, like in many of the textbook, this kind of problems are there. We are talking about these are the problems, like I got it from on the textbook of IIT Delhi professor, Professor Anil Ilyas. The B.D. Gupta textbook I was talking about, that is written by him with another professor from IIT Kanpur. So this textbook is very good, and if you would like to buy, it's not that expensive. It is only 700 or 800 rupees. Okay.
Swayam Prabha, Digital India, Educated India.